mainly the combustion problem now. So combustion problem of essentially having the species conservation equations rather, and energy equation, of course energy conservation equation. So this is what we want to now focus our attention on. We simply say flow field is prescribed, and let's not worry about the two-way interaction where we are assuming a density dependent temperature that influences the flow back again. The moment we'll just say as far as the combustion problem is concerned, the flow field is prescribed, and the question is it possible for us to now simplify this set of equations, right? What do you mean by simplify? How do you want to simplify this? Well, if you think about it, the species conservation equations is something which contains the capital V, the diffusion velocity, okay, the species diffusion velocities, which are in turn given by the multi-component diffusion equation. So you now have these n equations relating to 3n equations for the 3 components of this multi-component diffusion vector equation, okay, and those are in xi's, whereas this is in yi's. You now have to have an additional set of n equations to relate xi's and yi's, so that's complicated enough, alright. And then you have this energy equation which has like lots of terms that are on the right hand side, and each of those terms has lots of terms in turn and so on, so it's actually a very long equation. Our goal, believe it or not, okay, at this stage is to try to simplify these two sets of equations to look almost the same, not even similar. Is that possible? Can we even dream up of making this set of equations and a soup bowl of additional equations that it comes along with to look like an energy equation that is very long actually? So it is possible if you now make lots of assumptions, right, but the goal here is goal to simplify the above set of equations to reduce to a common form, right, reduce to a common form. In fact, let me tell you what the form that we are looking for is. Say a operator L, script L, of something like an alpha I, okay, equal to omega, and alpha, so this is I equals 1 to n, right. So obviously that's a species equations, right, species equations. Then let us suppose that we can now form a alpha t which is also equal to omega, okay, and this is the energy equation, right, and that's one equation. What we expect is alpha I should be related to yi in some way, okay, the primary unknown corresponding to the species equations, yi being the mass fraction of species I, and alpha t should be related to temperature in some sense, okay, in a fairly direct way. So long as we can actually establish those kinds of relationships and then say this stands for temperature, that stands for species concentration, and then you now are able to write these two equations in this form, okay, then we can now form then we can form beta I equals alpha I minus alpha 1. You pick the first one, okay, first of the alphas, okay, and then subtract that from all other alphas, and then you form a beta I corresponding to that, okay, and beta t equals alpha t minus alpha 1. You pick the first of these alphas, that's okay, alright, and then subtract from alpha t to form a beta t, okay. Now look for L, the script L, to be a linear operator, okay. Further, now if you really think about it, if you know some basic fluid mechanics, what you would expect is the nonlinear terms in fluid mechanics are primarily coming from the convective term in the momentum equation, okay. If you are prescribing the velocity field in the species conservation and the energy conservation equations, the convective terms in those species equations and energy equation are not they are not nonlinear, because your velocities there are known. The momentum equation, you had a product of velocity times velocity derivatives, and the velocity was an unknown. Anytime you have a product of an unknown and its with itself or its derivatives, then that shows up as a nonlinear term. But in the species equation and the energy equation, if your flow field is prescribed, that constitutes a linear term with a variable coefficient or a non-constant coefficient, that's all, okay. So as far as the convective term is concerned, which typically poses the nonlinearity in fluid mechanics in the momentum conservation, as far as the combustion problem is concerned, we can expect it to be linear, that's fine, alright. It's the other nonlinearities that we will have to worry about, like for example if you had a radiation term with a t to the power 4, or if you had this e to the minus ea over RUT, right, the exponential term of the reaction rate depending upon temperature and so on, those are the villains that we should be looking out for. But we expect that that should actually be on the right hand side, okay. The L itself could be linear. So if you now look for this L to be a linear operator, then we get L of alpha 1 equal to omega, but L of beta I equal to 0 and L of beta t equal to 0, here I going from 2 to n, because you can now subtract one equation from the other, right, or you can try basically subtract the first equation from all other equations and then now form your pairs of alpha I minus alpha 1 or alpha t minus alpha 1, and then plug in the betas. The right hand side is the same for all of them, so if you now subtract one from the other you get a 0, right. What is the advantage with zeros? We really like zeros, don't we, right. So the moment you now have zeros, first of all it means that this really means that we are now looking at homogeneous equations, right, which are a lot easier to think about when mathematically speaking when compared to inhomogeneous equations where you have source terms influencing the mathematical nature of the equations otherwise, okay. So first of all you are dealing with homogeneous equations, that's like a big boon, but implicitly we are also thinking it doesn't have to be zeros, but thank God the nonlinear term goes away. It was the right hand side that was nonlinear. We had this e to the minus e exponential of minus e by RT, which was a huge nonlinear term. I am trying to get rid of this in most of the equations. That was posing this stiff problem, right? That was the one that was actually trying to vary in a highly nonlinear fashion. That means it becomes very sensitive within a very narrow range of temperatures, and you have to take like very small steps in time or space or both in order to try to capture that variation somewhere there near the flame and so on. All those things we don't have to worry about for these equations. You still have that stuck in one equation representing this for the representing the severity for the rest of the set. And if you were to follow this, then here we call beta I and beta T as coupling functions, because they couple alphas together. Okay, beta i's couple alpha I and alpha 1, and beta T couples alpha T and alpha 1, right? So these are called coupling functions. So our goal is essentially to simplify the above set of equations to reduce to a common form, that is L of alpha is equal to 0 omega for both the species and the energy together, and then form the coupling functions so that we could actually get a homogeneous set of equations for a whole large number of equations except just one. Okay, sounds very incredible at this stage if you now think back on what the equations are, but the question is, how do we simplify? So this is the starting point, right? So we will now have to make a lot of assumptions, 11 assumptions to be precise, okay, which are mostly simplifying assumptions. So we now make these assumptions. And I want you to listen to this very carefully. There are 11 assumptions that we are going to make, alright. So it could be as if you can expect an exam question or a PhD qualifiers question. What are the 11 assumptions of the Schwab-Zeldovich formulation? Because they are the 11 assumptions. Okay, so we'll make those 11 assumptions, number 1. Number 2, whenever we make assumptions, keep in mind we get into the habit of questioning those assumptions. Are they good assumptions or are they bad assumptions? Are we making them mainly because we want to simplify the matter, right? Are they just simplifying assumptions, or are they physically tenable? That means, or can we justify them from physical grounds? Are they reasonable? Right? We will have to go through that when we make those 11 assumptions. The third, is there a way we can relax these assumptions? Some of them, many of them, all of them, right? So those will be your homework problems. Right? So I'll try to point out to you which are the assumptions you can relax and has been relaxed in the literature, okay, and I'll also point out to those literature, and then you can say, well, work out the Schwab-Zeldovich formulation with this assumption relaxed. That's like one particular question in an exam. Okay, so if you thought that you really mugged it up, then the next question in the next exam will be work out the Schwab-Zeldovich formulation with relaxing the other assumption. So you can keep doing this. Okay, and it'll be a pretty good piece of work actually. Okay, so don't take it lightly. It's very important. So I'm not going to relax all the assumptions. I'm not that crazy. Okay, so I'll point out to some assumptions that can be relaxed. So the first assumption that you're looking for is negligible body forces. We also should be looking for why we are making these assumptions, right? So, and then I'll also point out to some things that we are not assuming as we go along. So in that sense, to that extent, the formulation is general enough because we aren't making assumptions. For example, to tell you right away, we don't have to make assumptions about constant CPs. We could have temperature dependent species that are different for different species. Alright, that's great. That means you can actually get the adiabatic flame temperatures predicted fairly well, and then your formulation should be able to show the temperature in your flow field. So that's pretty good. Here the reason why we want to actually neglect body forces is it shows up in this set of equations, it shows up in the multi-component diffusion equation, right. So our goal is to try to simplify the multi-component diffusion equation to look like Fick's law, alright, so that we can directly substitute the Fick's law form of the multi-component diffusion equation into the species conservation equation right away, just like how we did it the first time for a binary mixture. Then we don't have to deal with the multi-component diffusion equation separately anymore. So the question is, what will allow us to simplify the multi-component diffusion equation to look like Fick's law? You remember the multi-component diffusion equation had 4 terms. The first of those was the one that was going to give rise to Fick's law. Then there was a pressure gradient term, then there was a temperature gradient term, which was the Soret effect, and then there was a body force term. So if you wanted to get rid of pressure gradient term, and then you have to get rid of the body forces term, and then you have to get rid of the Soret effect. Okay, so the first thing that we are trying to do here is to neglect body forces. Now if you went back and actually looked at that particular term, you had a Fi vector minus Fj vector. So you don't necessarily have to neglect body forces altogether. It was sufficient if the body forces were the same on all the species, right. So if not, okay, equal on all species. That's the assumption that we're trying to make. Okay. Second, negligible Soret and Dufour effects, terms involving dt comma I, right. This is the Soret effect is actually neglected so that you can simplify your multi-component diffusion equation into your Fick's law. The Dufour effect actually shows up in the energy equation, which also we try to neglect, primarily the justification being dTi over rho dij is typically fairly small. It has 1 order of magnitude less than unity, alright, therefore it is insignificant or negligible most of the time. Pressure gradient diffusion. Pressure gradient, I should say negligible pressure gradient diffusion, right, negligible pressure gradient diffusion. This term was looking more like yi minus xi times grad p over p. There are many ways by which you can neglect this. One, you simply say this term doesn't contribute a lot to the multi-component diffusion equation, right. No matter how much it is, you say it's very, you now evaluate it and find that it's very small. The other way of trying to get rid of this term is to say that you have equal molecular weights, that means yi's are equal to xi's, but that's a worse assumption than just saying that this is negligible, right. The third way of actually trying to justify this is just the previous class we found that for low Mach numbers the pressure is almost a constant. It affects only your flow field, but it doesn't really get into your combustion field a lot, right. So as far as the combustion problem is concerned, we could simply say the grad p is very small, right. That's the reason why we want to say the diffusion associated with it is even smaller, right. Okay, so that's reasonable. Now negligible bulk viscosity, and viscous dissipation. These are related but slightly different. Bulk viscosity effect can be neglected for incompressible flows. When you are now looking at low Mach numbers, we are now talking about low incompressible flows, so you can say that the divergence is equal to 0, so you do not really have dilatation effects coming in. So bulk viscosity, the effect of bulk viscosity is negligible, and this also shows up in the viscous dissipation term, and we are now saying the viscous dissipation itself is pretty small. If you now do an order of magnitude analysis, unless you are looking at situations of tribology, like when you now have a two surfaces that are actually in very close clearances and you had a fluid in between, like in lubrication and so on, or if you had like re-entry effects where your Mach numbers are so large and the boundary layer is so thin with a steep gradient, effectively you are looking for very large gradients of velocity. That is when viscous dissipation is significant, otherwise you do not have to worry about it, not typically in our application. 5. Negligible radiant heat flux, right, QR vector, right. Now of course this is going to be a nonlinear term if it were present, so you are going to have a t to the power 4 and t is an unknown, so you are now looking at a nonlinear effect there, so try to get rid of it, okay. But of course when can you say this is okay? So long as you are dealing with a gaseous medium, this is reasonable, okay. But the moment you have things like surfaces, you have to think a little bit harder. So if you have surfaces, you have to look for whether those surfaces are transparent or opaque, or if they are closer to black, if their emissivities are closer to black body emissivities, right. So if that is the case, then you can't neglect this. So not valid when in problems with phase interfaces, right. Not valid in problems with phase interfaces. Well, of course you will find in the literature there are lots of problems with phase interfaces that have been solved after neglecting radiant heat flux, and you still get good results. It's not terribly bad, okay. But in general the radiant heat flux is significantly small. You think about this, you now look at a flame, the fact that you are able to see the flame is because you have radiation coming and hitting you, your eye, alright, and you are like, wait a minute, I could see the flame only because of radiation, it is there. How could I say, how could I not take that into account? The answer is that it's quite small, okay, in magnitude, so you don't have to worry too much about this. 6. We assume a steady flow. We did that when we were trying to do on the low Mach number assumption, okay. So whatever we did in the previous class where we came to the conclusion that the pressure remains almost a constant for low Mach numbers is typically called the low Mach number assumption, right. So the low Mach number assumption was actually derived for steady flows, which is something that we also adopt over here. The point I mentioned the other day was you don't have to do that, okay, and similarly we don't have to do that here as well. You can relax, this assumption can be relaxed. You should be able to relax this assumption and derive a unsteady equivalent or an unsteady Schwab-Zeldovich formulation, okay. That's a homework problem for you. And keep in mind, what are we looking for? We are looking for a L, the script L operator, right, that should be linear, and typically the time derivative dou by dou t is a linear term, it's not showing up any nonlinearity, so you shouldn't have a problem with unsteady flows at all, so you should be able to relax this assumption. Then we say binary diffusion coefficients of all pairs of species, right, are equal. That is Dij equals D. Not even saying that we have Dij is equal to Di. That is to say, we are not saying that the binary diffusion coefficients are the same as the multi-component diffusion coefficients. Recall that the multi-component diffusion coefficients are derived quantities, whereas the binary diffusion coefficients are more fundamental, okay, which come from kinetic theory. But we are saying here that all of them are going to be equal for all pairs of species, and this is very important for you to be able to plug in your multi-component diffusion equation into a fixed law and then plug that into the species conservation equation. Otherwise what happens is you now have this xi is equal to grad xi is equal to some coefficient times vi minus vj, and you could derive fixed law only for a binary mixture where again dab is equal to dba, and since only two of them are there and they are equal, it's just as good as this assumption, and then you could have obtained fixed law. That's what we did before, but here we have to get past that for a truly multi-component mixture more than two species. Therefore this assumption is necessitated. Okay, the question is it okay? The answer is not terribly bad. Typically you have to start worrying about this assumption if you are dealing with things like hydrogen as part of your mixture, right. Let us say you had a mixture of hydrogen and hydrocarbon going through combustion, then the pairs of species involving hydrogen may typically have a higher diffusivity when compared to others, and then that is markedly different, whereas if you are dealing with most species of the order of the same molecular weights, not necessarily equal, you can expect that this assumption is a very reasonable assumption, not bad at all. Okay. 8, low speed or low Mach number. This implies that momentum equation reduces to P is equal to constant to first order, which means we could now say, let me get a flow field that is prescribed. I don't have to worry about solving for the flow field in addition to the combustion problem, so I am looking only at the combustion problem, so that is something that came from the previous class. 9, unity Lewis number. Right, so question is, what is Lewis number, right? So Lewis number Le is K divided by rho Cp d. Now keep in mind that d should really be like Dij in reality, alright. So correspondingly you should have a Lewis number that is like Leij, okay. But many times, as we have seen earlier, the Dij can be replaced by like a Di, that is like the multi-component diffusion coefficient rather than the binary diffusion coefficient, in which case again we will now have to recognize that Le should be written as a Lei. That means it is different for different species. So you are looking at a Lewis number that should be really species dependent, and many times people talk about a fuel Lewis number or an oxidizer Lewis number that are distinct from each other, right. So what is this Lewis number really telling us? K over rho Cp is the thermal diffusivity, and Dij or D here is the mass diffusivity, okay. So in SI units, K over rho Cp is going to be like meter squared per second, and the mass diffusivity also has the same units, meter squared per second, and therefore Le is a non-dimensional number which actually indicates the capability of a species to conduct heat just as well as it can diffuse. Right. So we are now looking at comparing the capability of the species to actually transport enthalpy as it can transport mass, right. So that they do not have to be necessarily the same, right, depends on how well it can conduct versus what its Cp is in comparison to how much it can diffuse itself as a mass, right. Why would you want to now compare these two? And what you are now basically saying is this should be equal to 1. This is a very important assumption. It can be relaxed, that is a good news, okay, but it is a very important assumption. Why? Because our goal is to actually look at the species conservation equation and the energy conservation equation and try to express them in a single form. How do you hope to do that if you don't expect the species to actually transport enthalpy just as well as it can transport the mass? Because these equations are essentially, remember, the convection, diffusion, reaction. These are the three things, and if you had some sort of an intuition, you would say that omega stands for reaction, not just because it is the symbol, but I have been saying that this is the one that is containing the nonlinearity in the Arrhenius term, that is essentially from the reaction. So if you now say convection, diffusion and reaction, and this is going to contain the reaction, then this is going to contain the convection and the diffusion. And sure enough, prescribing a velocity, you now simply have a non-constant coefficient for the convective term coming from the flow field, and the diffusion term should be linear just as well as the convection term. So we expect this to turn out to be linear. That means we are looking for two terms here, both of them linear, one of them coming from convection, the other one coming from diffusion, right. If now these two terms should look similar for the species conservation equation and the energy conservation equation, then we should be looking for the transport terms to be comparable. So if you now have a species which is actually diffusing so fast but it does not really conduct heat a lot, that means it is having a non-unity Lewis number less than 1, okay, then the transport terms or the diffusion terms in the species conservation equation and the energy conservation equation, they are not going to match up, alright, you are going to have a problem. So the only way we can actually try to get these two together to look similar is if you now have a unity Lewis number. In fact, in most of the earlier literature, I wouldn't say too early, like as late as even the 70s or 80s, or even now some works or many theoretical works that are getting published, they would make a unity Lewis number assumption, and sometimes when they relax this assumption and publish, they would even put it in the title, like they would say blah 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 for non-unity Lewis numbers. It's as if like it's a big achievement that they have done, that they relax this assumption, right. So that indicates the importance of this assumption, okay, that's indicating the importance of this process of what's called as preferential diffusion, when you now say the Lewis numbers are first of all not equal to 1 and not equal to each other. So if you now say preferential diffusion, you now allow for a oxidizer Lewis number to be different from a fuel Lewis number, for example, right, and sometimes you have this analysis that is done where you now assume that the oxidizer Lewis number is unity but the fuel Lewis number is not unity, or vice versa maybe, okay. So many times you need this assumption in different ways, but it is still possible for us to think of writing not exactly in this form of course, but you will still be able to write something like a convection, diffusion and reaction, okay, except that the diffusion terms alone may be different by a factor of the Lewis number if the Lewis number were non-unity, and that would be like the counterpart of the Schwab-Zeldovich formulation. We may not be able to form coupling terms, alright. So it is possible to actually work with non-unity Lewis numbers and proceed in the manner, if you now make all the other assumptions, relax this assumption and see what happens. It's worth pursuing that. Okay. Then we assume a chemical changes occur in a single reaction step. Single reaction step, sigma I equals 1 to n, nu I single prime script mi gives rise to sigma I equals 1 to n, nu I double prime script mi. Just one step. We do not entertain multi-step chemical kinetics, okay. That helps us in dealing with trying to split the enthalpy into the formation enthalpy and the sensible enthalpy and deal with the formation enthalpy term. So you now get a single heat release rate term because of the single step kinetics. So essentially what's happening is you now assume like there is only one reaction that's happening in the flame, although there are lots of reactions that are happening, but if you were to entertain many reactions, each of those reactions is going to give rise to a heat release, right, and some of them could actually absorb heat. So there's like a net heat release that you should be looking for, whereas we want to deal with only one heat release rate term, not multiple heat release rate terms, okay. So that's what this assumption lets you do. Try relaxing this either, okay. So we will talk a little bit about that as we go along. The 11th assumption is a fairly straightforward assumption, no external heat flux. That is Q dot equal to 0. Q dot is equal to 0. This was showing up as a solitary term only in the energy equation. It was not there in the species equation. So if you now keep this, then it's not possible for you to make them look alike, right. So we have to get rid of this. This is reasonable again, okay. You get into this kind of situation only in some oddball cases where you have to keep some externally heat generating mechanism or machinery within your domain, alright. That's like some electrical heating or nuclear heating or let's say arc heating or something of that sort, which is not due to the combustion, alright. Therefore we don't have to worry about this under most circumstances. Good. So we now went through the 11 assumptions. Now we go through the algebra. How do you crank the machinery to make this look like make these two equations look alike? So it's going to involve some magic, alright. So you have to kind of watch out for how these manipulations happen, and we'll go through this now and maybe in the next hour as well, and maybe by the end of then we should be getting there to see whatever we are looking for. Yeah. Yeah.
But in that case, we can't couple the equations.
Correct.
So what's the point?
The equations can still be considered linear.
I won't be able to solve that.
If you now had like two species equations, you assumed a non-unity Lewis number, all right, but the Lewis numbers were equal, right. You now have two species equations which are still linear, which can be where you can still form the coupling functions, alright, and then you have the Lewis number, the equal Lewis number for each of those still sticking together. It's only that you can't make it look similar to the energy equation, So as far as the species equations are concerned, they can begin to look similar, right? And I am still saying I am not having a unity Lewis number, I am having non-unity Lewis number, but non-unity but equal, you see. So there are such conditions. There are also other situations where it's possible for you to deal with, like saying one of the Lewis numbers is equal to 1 but the other Lewis number is not equal to 1. There you try to couple that equation with the energy equation, where the Lewis number of that particular species is equal to 1 but you keep the other one, okay. So typically we will, in fact what we will find is, in the problems that we deal with, let's say we will want to do like a premix flame or a diffusion flame and so on in due course, our starting point will be the Schwab-Zeldovich formulation, okay. At that time we should look forward to seeing if we can relax the Lewis number unity assumption for some of the species, or say equal Lewis numbers but not necessarily equal to 1 and so on. The point I wanted to make was, what you will find is we will pick and choose some equations to form coupling functions and not worry about the others, alright. So this will depend on the way you assume your Lewis numbers, alright. So it's pretty interesting the way we can deal with it, okay. So now given the situation, we now start with the overall continuity equation. It simply leads to divergence of rho v vector is equal to 0, right. We still deal with 3D, we will have a vector form of equations, so that means it's a three-dimensional formulation, nothing no assumptions on that, right. Now let us look at energy equation with all the assumptions that we have made. So no q dot viscous dissipation phi and dp over dt. You get this dp over dt only for compressible flows, because we are now looking at a low Mach number situation. You shouldn't have to worry about this. Then you have a rho v vector dot del h is equal to del dot k grad t minus del dot rho sigma capital K equals 1 to n hk yk capital Bk, okay. This was coming from your divergence q vector, and q vector had k grad t okay, k grad t in fact minus k grad t, and you had this term, and you had the Duffer effect and the QR. You have got rid of the Duffer effect and the QR. Outside of the grad q dot you had the body force work, you had the viscous dissipation, and you had the pressure work. So all those have gone, so we are left with only these two. Keep in mind, what are we looking for? We are looking for getting this equation to look like convection, diffusion, reaction. Okay. Now the reaction rate term is actually embedded in here. This is going to be now written as h is equal to sigma yi sigma yk hk, where hk is the specific enthalpy of species k, which can in turn be written as delta hfk naught plus the sensible enthalpy for that, right. And then the delta hfk naught term is the one that is going to contribute to the heat release. So that's where the reaction term is coming from in the energy equation. Okay, the job of the reactions in the energy equation is to give rise to the chemical heat release that is embedded in here, right. So this contains both the convection term and the reaction term that we are looking for. This is the diffusion term that we are looking for from an energy point of view. This is essentially the energy transport term, okay. That's something that we have to deal with. That isn't something that we were looking for, and it is not there in the species conservation equation. Okay, but you do have a capital Vk showing up in the species conservation, which will now have to be replaced by a fixed law having a gradient Yk. So this is going to be a little bit more involved than it seems. Okay, so now note that H is equal to sigma Yk Hk. All right. Now therefore sigma Yk Hk divergence rho v vector equal to 0 starting from here. I just multiplied these two, right, and right hand side of this is equal to 0, therefore this should be equal to 0. Now add the above to the energy equation, right, and then you have, so what do you get? If I can now add this to this, which is essentially 0, okay, I can now try to take the divergence out. You see, you have a rho v dot grad h, here we have a, this is h times divergence rho v. So if you now add these two together, we can get a divergence of rho v times the h, you see. So I can get this divergence of rho sigma hk yk, and then what happens? Why did I want to do that? Because I have a divergence of rho times this, right. I should now be able to combine these two, v plus capital Vk, right, and I also note that this is like a divergence term, and so if I now have a divergence that is outside, I should now be able to write this also inside, k gradient T equal to 0. Now let's call this A. Keep this. Why would I want to do this? Because I am now going to begin to realize that Hk can be written as delta H of k naught plus the sensible enthalpy, alright. Delta H of k naught times Yk times V. If you now have this term, I can now try to look for supplying the species conservation equation to get its right hand side to come and plug in here, okay. So I will now be able to write something like a, for the term that has the delta H of k naught alone, I should now be able to write this as like a sigma Wk delta H of k naught. So Wk is coming from the right hand side of the species conservation, which will now look, whose left hand side is this. I plug the right hand side of that here, right, for only that term which has the delta H of k naught. That will simply mean the chemical heat release rate term is nothing but the reaction rate term times the heat release from that reaction. That's correct, because a reaction is going to give rise to a certain heat release per unit mass of the fuel or any of the reactants. If you now multiply that by the rate of change of that species mass per unit time, right, then you should get the heat release, the heat release rate. So we will try to look for that manipulation soon. So we now say species conservation can be written as divergence rho yi times v plus capital Vi equals Wi, I equals 1 to n, right. Now let us just start this saying this is B, okay. So what I am basically saying, and I will stop. So basically note that Hk equals delta HFK naught plus integral T ref to T Cpk, small cpk dt, right. So this is the sensible enthalpy term, this is the standard heat of formation. Therefore if we now plug this in here, right, in the energy equation, and notice that you now have a rho yi v plus vi combination with the delta HFK, wherever you have that you now put your wi. Well I guess I'm sorry, I missed symbols, so let us just have k instead of I, capital K, right. So what you are looking for is whenever you have this combination, you now try to put wk whenever you have delta HFK naught over there, and if you now split this, then what is going to remain is only this term on the left hand side. The right hand side is simply going to be delta HFK naught times wk sigma of that. So the energy equation becomes divergence of rho integral rho, we now say sigma, well actually I think I can get rid of the sigma for the first term. If I now try to pull this v out and open up this brackets, sigma hk yk will simply again be h, and that will correspond to simply a rho Cp. Notice that we don't have a k over here because we basically summed over there. That's plus. So we are now looking at only the sensible enthalpy term kept on the left hand side. So we now sum over, the Cpk becomes Cp, but then you have to keep the Cpk as it is with the capital Vk. So we will just do that. Sigma k equals 1 to n yk capital Vk, and then keep your sensible enthalpy term as it is with the Cpk dt, and then of course you also have this minus k dt grad t that you have to keep, minus k grad t. And what we did was to get the standard heat of formation part to the right hand side, and notice that that part alone actually stands for wk. So you can now easily write this as minus sigma k equals 1 to n delta hf naught k wk. So this obviously is the chemical heat release rate term, because this actually tells you how much is the heat that is released, right. So this is actually like joules per kg, and this is like kgs per meter cubed second, right. So if you now get rid of these two, k kilograms, this is the amount of heat released per unit mass of that species k, and this is the mass of species k that is getting converted per unit time per unit volume. So together this will actually mean joules per second per meter cubed or watts per meter cubed, you see. So this is the volumetric heat release rate, right. So that's how, and then you sum it over for all the species that are getting produced or consumed, okay. So this effectively is now, for the first time we are now beginning to see the chemical heat release rate isolated in the energy equation here, okay. This is a good point to stop.